For problem 38, we're trying to determine whether the series is convergent or divergent. And so we're given this series here, where it begins with k is equal to 1 to infinity of cosine of 1, and all of this to the power of k. And we can see here that this is a geometric series because we have some number, which is a ratio, raised to the power of k. So we can see here that it is possible for us to find a sum, but only if the absolute value of the ratio, so the thing that's being raised to the power of n, is less than 1. So cosine of 1, it depends whether we're considering this to be radians or degrees, but it works both ways because cosine of 1 in degrees is about 0.54, and cosine of 1 in radians is about 0.99. So either way, what you consider this, it does work because both of these are less than 1. We're going to use degrees for this exercise, but you could also consider it the other way around. So now that we know that this does converge, it is a geometric series because the ratio is less than 1, we now have to find the sum. So we're going to use this formula here highlighted in yellow. However, we're not quite ready to just plug the stuff into the formula because our formula for it to work, it's indexed at 0. So what this means here is that when you plug in 0 for the first index, you're going to get 8 times r to the power of 0, which is just a. And this is reflected over here in the expansion, where the first term is just a constant by itself. So in this case, it would be 1 because we can't see it there. And then the second term would be a times the ratio to the power of 1. The third term would be a times the ratio to the power of 2, and so on and so forth. And we can see that it doesn't work in what we have here, because if we plug in the first index, what we're going to get in this expansion is we're going to get cosine of 1 to the power of 1 plus cosine of 1 to the power of 2, and so on and so forth. So you can think of it as being out of phase, where the first term already has the cosine to the power of 1, but that's not what we want. We want it to evaluate k is equal to 0 for the first term. So what we're going to do here is we're just going to split out this cosine of 1 to the power of k. We're going to split this cosine of 1 to the power of k. We're going to split this into cosine of 1 to the power of k minus 1 times cosine of 1 to the power of 1. And the reason that we're allowed to split it up is because we're just multiplying, right? And remember that when we multiply, we add the exponents. So if we were to add them, we would have cosine of 1 to the power of k minus 1 plus 1, which is just cosine of 1 to the power of k. So it does work out. So what we're going to do here is we're just going to rewrite this by splitting off the power. So we have this is equal to the sum from k is equal to 1 to infinity of cosine of 1 times cosine of 1 to the power of k minus 1. So once I've split this off, I can see that it now works, because if I plug in k is equal to 1, the first power that's going to evaluate, it's going to be cosine of 1 to the power of 1 minus 1, which is 0. So now everything matches up correctly. So once we've rewritten this, to use the formula, because remember our formula is, let me highlight that, is a over 1 minus r. So let's identify what is what. So a, which is the thing that's being multiplied, we can see that that's just cosine of 1. So a is cosine of 1. And the ratio, the thing that's being raised to a power, is also going to be, r is also going to be cosine of 1. So once we have this, let's plug it into our formula. So our formula is a over 1 minus r. So the sum here of k is equal to 1 of cosine of 1 times cosine of 1 to the k minus 1 is going to be a, so cosine of 1 divided by 1 minus r. 1 minus cosine of 1. And that is it for our series. It is convergent, and because the ratio was less than 1, and we just had to manipulate it a little bit to get the index to match up. And once we did, we could plug it into the formula for the sum, and we get cosine of 1 divided by 1 minus cosine of 1.